K in K. Ah, well. And you just don't say anything. Okay. Right. So I suppose I was in the discussion somewhere in the 60s. So let's yeah, there are various strands historically that one has to take into account. And I was still discussing that finite generation for AG, and this is so we. I tried to explain that the correct class of G's to consider is the class of reductive groups. So if G is reductive, there is such a theorem. A theorem. And if not, then not. In other words, if you have a group which is not reductive, there is some algebra which is finitely generated itself, but the ring of invariance is not finitely generated. Now let me briefly recall what reductive is, just to be on the safe side. Yeah, so the unipotent radical of a linear algebraic group, a notion which I have maybe not yet defined, but such details will come later, is the largest connected unipotent normal subgroup. Now I think the only thing to explain here is unipotent. So U is called unipotent if it has a faithful representation but let me just say by matrices of the following shape. Zeros, then ones on the diagonal, and then something here. So the matrices of this shape are called unipotent. Matrices conjugate to such a thing are also called unipotent. But the fact is that if you have a group which is unipotent, then there is a representation and a choice of bases in the representation so that the corresponding matrices all look like that. And so that's the unipotent radical. And then G is called reductive if the unipotent radical is trivial. So that's the class of groups for which we have finite generation theorem. Over the complex numbers, this is the story I told with the maximal complex subgroup and the averaging and and the complexification stuff. But so now in the 60s, you have Mumford's book on geometric invariant theory. Where he needs a theorem like that for a group, for the case that the ground field has positive characteristic. Okay, so let's say that the ground field is that the ground ring is a field, and that its characteristic is P, and that is a positive number, so it's a prime. Then in the introduction of his book, he formulates. So this is a 1965 book. He formulates a conjecture which consists of two parts. The first part was solved by Nagata and that was published in 1964. So this is the usual confusing things with dates. The time that something is published is usually the official date that is attached to something, but clearly Nagata knew about the problem before the book appeared. Yes? So there was two halves, and the other half took much longer. It was Habush that so at that time I was still in high school, but here I was at the conference where Habush explained his proof, and I did not attend. But I was aware of him, of what the theorem was, and that people like Borel were trying to shoot holes into the argument and were not succeeding. So this was definitely that was quite a nice result. So let me try to phrase it. So Mumford introduced a notion which well, he didn't call geometric reductivity in the book, but that's how it became known. So you have geometric reductivity. And his conjecture was that reductive implies geometric reductive. Well, maybe reductivity implies geometric reductivity implies finite generation. Now, this is what Nagata did, and this took much longer. So this is Habush. Now, okay, so what's geometric reductivity? There are various versions in the literature. You have various equivalent conditions that are all now called geometric reductivity, which is a bit confusing to me when I want to go to a different setting where the ground ring is no longer a field, because then it matters a lot which of the formulations you pick. So let me look at what Nagata actually needed. And so Nagata needed the following thing that Franjou and I have baptized power reductivity. Just to have a new name for an old concept and still unambiguous, because no. So what's power reductivity? Well, a short way of phrasing it is as follows. G is power reductive if whenever G acts, well, algebraically, of course, on a commutative, of course, K algebra A with an ideal J or I, let's say J, that is a submodule, so that is invariant. Yeah, so you have a set is invariant if every element of the group sends a set to itself. So that's not the same notion as being uninvariant. An invariant is an element that's invariant. So that's a singleton invariant set. So but here we have just an ideal that's invariant. So that you can, you have a map from A to A mod J, and this it then has a G action compatible with that, right? I mean, that's the way it is. And so now you can take invariance, okay? Now if you had a Reynolds operator, then you would immediately know that this subjects to that. But in characteristic P, you do not expect a Reynolds operator. So what you can hope for instead is that whenever you have an invariant here, let's write it as F bar to indicate that it's modulo J, then there must be an N, at least one, which of course depends on the F and on the A and the J and everything, so that the nth power lifts to the big invariance in the big ring. So that's what we call power reductivity. So power reductivity with exponent 1 is what you have of the complex numbers, because there both A and A mod J as representations split as a direct sum of invariance and other stuff. And oh, that's, yeah, that's true. That much is clear. And now the the fact is that the other stuff cannot go to here, but must go to the other stuff, because the other stuff consists of a direct sum of irreducible representations without invariance. Linear? Well, it's linear on, I mean, this is a vector space A. In that sense, it's linear. K is yeah, today is the field.
And G is an algebraic group
Over K, yes. Yes, K is the base field, and everything is over K. That has nothing to do with this K. Yeah.
So for characteristics, do you have Reynolds operator?
Yes. You always have. Well, you see, so the statement is that well, you have this maximal compact subgroup, and we're doing algebraic representations, and that means that any representation, even infinite dimensional, breaks up into direct sum of finite dimensional irreducible representations.
For characteristics, when you don't have what you are always have for general field of characteristics.
Yeah, well, it doesn't make any difference because I work in algebraic setting, and then extension of scalars is an innocent operation. You can just go. I mean, it's really not a serious problem. Well, yeah. I mean, you use what? Am I cheating?
No, you can say Lefschetz principle.
Lefschetz principle, yeah, whatever. But so, yeah, in any case, for the kind of stuff that I'm interested in, you can always pass to the algebraic closure of your field, and so you don't have to worry about any subtleties that come under the name non-split or under the name isotropic, or I mean.
You're assuming that K closure can be embedded inside C, or
Lefschetz principle. I mean,
K if
Lefschetz principle says that it doesn't matter if you're doing algebra. I mean, yeah, no, you see, in a proof, I mean, basically only finitely many elements of your field are going to be relevant, and so you can look at the subfield generated by the elements you actually need, and that subfield can always be embedded into the complex numbers. I mean, it's something like that. I mean, there's really we really don't care about that. Okay.
but is there any algebraic proof without going into that integration and so on?
Huh? No, of course you can develop the theory of algebraic groups without analysis. Go read a book by Borel or Springer and enjoy. But it certainly is not how historically it came about. But anyway, so I think this is more or less. Oh yeah. So why did Franjou and Van der Kallen want a specific formulation? That's because you can now extend everything replacing the base field by a general commutative ring, well, say Noetherian, and then it still works. So by choosing the correct, well, of course, what still works is Habush's argument still works, basically. I mean, that's well, it's a simplified story, but I may at some point want to say more about that, but not today, because I want to say more about, yeah, I always say somehow want to end up naturally with my conjecture, right? So this was the, so I suppose that this sort of covers what the finite generation of invariance part has to tell us. And now we go to a different branch, Well, we already had Emineuter. And recall that she had a finite group. Her base ring was just commutative Noetherian. Her algebra was commutative and finitely generated as a K-algebra. And then what she said was that this one is also finitely generated as a K-algebra. Now in Leonard Evans in 61, extended this result to the full cohomology ring. This one is finitely generated as a K-algebra. So same K, same A, and notice that. Okay, so this is it's a graded commutative ring, not to be confused with a commutative graded ring, K-algebra. So graded commutative means that it's graded, and you have the following rule: x times y equals -1 to the degree of x times the degree of y times y of x, if x and y are homogeneous. And so this is an algebra, and it has, and the H0, that of course is just what Emineuter was talking about. So here you have a graded algebra, and the degree 0 part was already known to be finitely generated. But what Evans says, no, the whole thing is finitely generated. And at about the same time, Venkov did this. Huh? Finite group. Yeah. So the theorem of Evans has the same data as the theorem of Emineuter.
Do you want A to be flat or something like that?
I don't. I believe cup products exist without flatness, because you just have cochains. You cup them. No, I don't think there was a flatness condition there. Okay, now this is, so Venkov had it only for a trivial action. And so usually,
No, but what was G?
same G. Finite. Yeah. But so usually people say that Evans and Venkov proved the same theorem, but from my point of view, that's not true at all, because I definitely need this theme, not that. Okay, the reason that people emphasize this one is that if you now look at how the story continues, that one is playing a very big role in. So next thing that happened was that Quillen picked this up and Quillen determined the cool dimension of this thing. Of H star GK. And he said, well, okay, this is not a commutative algebra, but it's not my fault that the textbooks on commutative ring theory don't treat graded commutative rings. So I'll just say rewrite your textbooks. But an alternative is what is usually done is to say, well, let's just take the even part, because whatever Quillen means, it has the same cool dimension, and now it's a commutative ring, and we can just use our old textbooks. Okay, yeah, because the there are two cases. One case is that the characteristic is 2. In that case, the sign drops out and there is no problem. Or the characteristic is odd, and then it actually follows from this that if the degree of x is odd, so if p is odd and the degree of x is odd, then this implies that it cups itself to 0. Cup is the operation in that algebra. And so you know that for cool dimension you don't care about nilpotents, and so it's not. Okay, so what's the answer? The cool dimension is the rank of the largest elementary abelian P subgroup. So in other words, you are looking for a subgroup of the form Z mod PZ to the power R, and the largest R, that's the cool dimension. That was Quillen. That was 71. Then Chouinard did something. If M is, well, let's say a finite dimensional G module, G is still finite, right? And we're still in characteristic P. Then you can detect if M is a projective module by inspecting the restrictions of M to elementary E elementary abelian P subgroup. Okay. Then Dade.
What does specifically mean? Inspecting means checking the projectivity. What does it mean?
Well, by knowing what the module structure is on the elementary abelian for the restriction, you can decide.
Oh, there's more information that is required to decide projectivity, or just the projectivity of the module?
The projectivity of the module is decided by the restrictions.
Oh, by restriction. Like say inspecting event, some explicit structure results.
Yeah, you just have to look what they look like. And I'm,
Just a question.
yeah, I don't, I suppose they just have to be projective when restricted to the elementary abelian subgroups. But, I mean, this can be looked up. Yeah, so maybe, does everyone know what the projective module is for a G module? So it means that this is exact. So if n goes to that is exact, that is the same as m is projective. And in a more in a diagram way, so it means that if you have n surjective to n double and you have m here, then there always should be a map that way which makes the diagram commute. That's projectivity. So we will, and yeah, so P is, yeah, oh yes, P is the characteristic. So characteristic of K is P is positive. You're right, I switched. Evans' theorem didn't require that. But jumping to Quillen's theorem, I'm back in the case that the ground ring is a field of characteristic P, which is positive. And it's the same P as the P here. It's the elementary P subgroups. I mean, that, you can only say that if you have a P. That's okay, so that was Chewy now. Eh? Now Date's lemma. Well, so we have such an M again, and now we notice that from the X algebra of K with K, you can go to the X algebra of M with itself by just tensoring with M. And this thing here, that is a different notation for what I just wrote. And so in any case, so what you have a ring map which is coming from, so you're given a module, you get a ring map. The ring map has a kernel which is an ideal. If you factor out that ideal, you get a new cool dimension. And this is called the dimension of the support of M. Yeah, so shall I write this? So put J is the kernel of that map, and the dimension of the cohomology divided by J. And now you can say, well, Quillen is right. You don't want to say even all the time. I mean, this is a nuisance. So this is called the dimension of the support variety, the support of M. And now Date's lemma says that this is 0. This is 0 by Date's lemma if and only if M has finite projective dimension. So what does that mean? A finite projective dimension, that just means that if you have M, you can always hit it with a free module. Hold it. The dimension of this quotient ring.
No, but support to M is over kg. I'm confused over.
The support of M is this variety, sort of.
So that's a definition.
That's the definition. So the terminology is this is called the support variety, or at least it's the coordinate ring of the support variety. And when you factor out J, you're looking at a subset of the support variety, and so you have a duality between algebra and geometry. And you can say what dimension is on the algebra side or on the geometry side. And on the geometry side, it's by definition what it is on the algebra side. So you might as well stay on the algebra side. But the spectrum of this thing, that is the support of M.
This is for an arbitrary M, this definition.
Well, let me keep M finite dimensional or something.
No, but there could be another sense, like it's star GM is a finitely generated module over star GK.
If this is finitely generated, yes, it is. Yes.
There is a notion of support of that.
Wait, is it? Is it finitely generated? Oh Lord. Check, Benson. Okay, so what? So what is the story? The story is, well, it goes on a little bit like this. But so these people in finite group theory were getting more and more impressive results. And so somewhere along the line, people working in representation theory of algebraic groups woke up and said, this looks so nice, we should join that. And so now, in order to join that, we... I was saying what finite projective dimension is. Yes. If you can stop after finitely many steps with your exact sequence of projective modules, then you say that the projective dimension is at most D. And when you have to keep going, it's not finite. And yeah, so the story was we wanted to join this activity because well, there is such a thing as G. It's a finite group, but in our context, we had the notion G is a finite group scheme. And the obvious plan was to first go and prove the theorem of Evans with group replaced by group scheme. And so we were sitting at a conference, and so someone asked, who's going to do that? Any volunteers? And so there were 2 or 3 people who said, yeah, that should be easy, let me have a look. So at the next conference, it was asked, I didn't hear from anyone that it had been done. Did you actually try? And so some people spoke up and said, yeah, we actually did try, but I didn't quite get it. It just looks a little harder than it seemed at first. Okay, and well, to cut a long story short, in where is it? In 19, a lot later, Friedlander and Suslin finally cracked it, and they, as they say in their introduction, the problem proved surprisingly elusive. And so they had to invent a new branch of mathematics, basically, to get the problem solved. And that's I think is a good moment for the break. The new branch of mathematics is called strict polynomial functors, and which has to be extended to strict polynomial bifunctors if you want to do even more, like my conjecture. But so they needed the strict polynomial functors business to just do step 0 in the program that I was, after the break I will say a little bit more about. But that was, but it was really surprising. We thought that there was really finite group schemes and finite groups. In our mind, they were basically the same thing, but just a little formalized, just extended to say it in the Grothendieck way rather than the old-fashioned way. But it seems it turned out to make such a big difference. It was really strange. Right. So we had Dade's lemma, and we keep the same situation: finite group over a field of characteristic P. Let's just tell some more. Next theorem. So I didn't write down at what conference the problem was first brought up, but somewhere around this time, I suppose, because here, Alprin Evans, they showed that dimension. We just had Dade's lemma, which was about the case of dimension 0. And dimension of the support variety, the dimension of the support of M corresponds with the complexity of M, which is defined something like this. You take projective resolution and you try to keep it those projectives small. So if a free module of rank 3 suffices, you don't take rank 30. You just keep it minimal, and then you look at how fast they grow anyway. So the complexity is the rate of growth that is necessary. And there's undoubtedly a formula which tells you should look at that exponent or something, but I'm not sure.
The geometry of this object has no significance. The geometry of this, I mean, this is. You can think
No,
of
what
it
this says is that the geometry has significance.
because of this.
The dimension.
No, there is no sheaf theoretic object on this geometry associated with this M, whose genuine support might look like this.
Well, I suspect this actually may be viewed as a sheaf on that. Because, well, I mean, if you look at the even part, what we're really looking at is we have then this thing is a module over that commutative ring, and so there is a sheaf. There is a sheaf, but one would have to check if people actually worked in the area like Benson to yeah.
Say something about the singularities in that.
The singularities, I don't, I,
It's saying that it's smooth if and only if the support is zero dimensional.
smooth? I didn't say smooth.
No, but it's finite. It's M was finite projective dimension.
Yeah, well, I wouldn't call it smoothness, but there really is a. So what we're learning is that there is an interaction between the geometry of the.
It's more like a vanishing theorem for M in some sense, right?
Yeah. Yeah. Okay, then we have Clausen. And here you can also define a rank variety and without cohomology. And so now the conjecture was the two pictures agree. And then Avoon and Scott in 1982 actually proved this Carlson conjecture. Okay, so, and if you want to know more details about this stuff from someone who actually knows it, just start reading in Carlson's book, in Benson's book.
There's a discrepancy in the dates. Yeah. The conjecture is made after it has been proved.
Hey. Yeah. Oh well. Maybe Benson says it better. Chapter 5, overview and historical background. In here you can find very nicely a description of the contributions of most people. The one which is, there's one that's not explained very well, and that is Benson himself. But oh well. No, it's too difficult to find. Well, anyway, so this is roughly the story. So this was the thing that that triggered the interest in the finite generation problem for finite group schemes. And yeah, let me just give you one example of a finite group scheme before I introduce group schemes, just to have, it will be it will be a stupid example in the sense that it will be an example where you have a Reynolds operator, so there is no problem. But let's give the example anyway. So an example, we still have the characteristic is P, and we're looking at the category of K algebras, which for me will be always commutative with 1. That doesn't mean that all K algebras are commutative with 1, but the category of K algebras is consists of those. So if I have a K algebra R, then I can associate to it what's called mu P of R, which is by definition the R in R for which R to the P equals 1. And if you can generalize this, you can take mu Pn, and then you get a Pn here. Now this is, so this group scheme of P to the nth roots of unity has the property that when R is a field, then this doesn't give anything. Well, it gives the unit element. It's always a group, but the group is, so the group scheme is invisible if you sample it with fields. And that's typical of these finite group schemes that we will be interested in. They will not be visible with fields, and therefore the naive picture where you think of an algebraic group as somehow sitting inside the GLNF with F big enough will not be helpful. Okay, that's so that will be yeah. So this one has the has actually no higher cohomology because of the Reynolds operator. But so in this case, the problem is not surprisingly elusive. It's the problem is it's just easy in this case. So that was one strand. Now I want to talk about some other ingredient. Yes. Okay. So Friedlander and Suslin had to invent these strict polynomial functors, but some things happened before that, which can serve as background for what they were doing. Well, of course, it starts with 1901 at Schur's thesis, Isaiah Schur. And in this thesis, he introduced this, what's now called the Schur algebra. And well, I suppose he did it over the complex numbers, but the thing works over any commutative ring. So let's take a field. Okay, a field. Let's say k equals k bar for now, so that we stay in the naive picture, because we can. I mean, to understand what Schur is about, you can safely just look at the at GLNK. GLNK is just a group. You don't have to think about it as being a variety or a scheme, or I mean, you just think of it as the group of n by n matrices. But you it's called G, but you have its coordinate ring, and it's the coordinate ring as elements the functions. Well, is it? Yeah, I don't know. G11, G12, up to Gn, and then 1 over the determinant of Gij. So what am I doing? I'm writing an element G in G as a matrix, because that's what it is. And then the G11 is the function on the group whose value is the matrix entry at place 1, 1. And so this is a localization of a polynomial ring in n square variables, and we think of them as the algebraic functions on my group. But the G is sitting inside the algebra of n by n matrices. Okay. Now, if you have a representation of G, it may happen that it actually comes from a representation of that full matrix algebra. By representation of the matrix algebra, I just mean a module, a left module. So let's so call a finite dimensional representation M of G polynomial if it extends to Mn. My field is called K. So, yeah, so what does that mean? Well, I've taken my field to be infinite. So, so when you have a function on the group given by some polynomial expression, you can recover the expression from the function because the field is infinite. There are no two expressions that are different and that give the same value. You don't have that for infinite fields. So I can confuse, so I can say, okay, I can just look at a function and see if it's polynomial. So this is then equivalent to, so equivalently, if V is in M and GV is F1G V1 plus FR G VR with VI a basis of M, then the Fi should be inside the polynomial ring without inverting the determinant. Because if you need the determinant in the denominator, there will be a pole where the formula does not extend to the full matrix algebra. So now, if all Fi are homogeneous of degree D, we call the representation polynomial of degree D, polynomial representation of degree D. So that's, let's do examples.
So this is in contrast to what is called a rational representation of a field.
Yeah, rational refers to fractions, and then you allow the denominator to be the determinant. And polynomial means that no denominator. And now, so let's do some examples. We have, of course, V equals Kn, the defining representation. where you simply take n by n matrix and a column of length n and you multiply. That one is a polynomial representation of degree 1. If you inspect the formulas, you see that they are of degree 1 in the matrix entries. Okay? Now then it's easy enough to get a representation of degree 3. This one has a sub-representation by taking invariance on the permutation of the 3 factors. This is called the third divided power. And dually, you can take, instead of invariance, you can take co-invariance, and so then you get the third symmetric power, which has elements that look like this. Let's say V1 was already the basis element, right? So let's say W1, W2, W3 plus 12 W4, W5 squared, that kind of expression, where the W's are from the vector space V. So, yeah, so, okay. If you're not familiar with the with symmetric algebras, then I can tell you that you're wrong. You are, because once you've chosen a basis in your vector space, the symmetric algebra is just a polynomial ring, and you know polynomial rings. So you actually know symmetric algebras. But it's wrong to think of them as polynomial rings, because for the same reason as it's wrong to think of a vector space as a vector space with a chosen basis. Because I want my group to act, my group will usually not respect the basis. It will not send the basis to itself. So you should take a more abstract point of view. And the right way is, of course, to use a universal property. In other words, we need to get used to invoking Yoneda's lemma whenever we can. Everyone knows what Yoneda's lemma is? Okay, who does? Okay, that's good. That's clear.
I think we should revise it.
I actually have not. I mean, Yoneda's lemma is a very important principle that you need a lot, and I keep forgetting what it says, but the proof is so short that that's not a problem, and but it's ridiculously important, and you have to use it all the time. But so here it is. We have a category C, and let's consider a functor f from C to the category of sets. Well, yeah, that's one. Now let's see. Consider a more concrete functor. Namely, let's take an object C. I just write C in C. That means C is an object. I'm assuming you've seen categories, yes? Okay. So now here's the functor. X goes to home C Cx. Yeah. Okay. And so now I have two functors from C to Z, and I can ask myself, what about the natural transformations? And now I have, yeah, let's call this one H upper C, okay? I write the C up there because it's contravariant in the C. I think that's a good decision. Now is it this way? Would that be right?
Does it believe in algebra or geometry?
Huh? I know we know that it's algebra and geometry, but here we're doing category theory, right? I mean, there's, I think this is right. Okay, so let's try it. So, what does equality mean? Huh? Ah, oops. Yeah, of course. Yeah, so one check that this might be the right formula is that this was contravariant, this thing was contravariant in C, but now you're in the left spot, so that's contra, and this side it looks covariant. So I think I'm on the right track. Yeah. So, and equality, of course, means there is an isomorphism and there's only one reasonable one, and these sets are basically the same. So then the way to do it is you would need maps from left to right and from right to left, I suppose. So let's start with a natural transformation. And I want to end up in C. Well, that's easy. I then have a map from, given a phi like that, I have a map from here to there. Now this was just the homomorphisms in my category from C to C. Now I only know it's a category, so I know only one element that's certainly there. It's the identity. And so the identity is sitting in here, and it goes somewhere, and that's where it goes. Okay, so I have a map from left to right. Let's see if I can think of a map in the other direction. Suppose I have a y in here. And now I'm looking for a natural transformation psi from HC to F. So I'm looking for that. And so I should explain how to go from here to there. And so what is an element in here? That's a morphism from C to D. And I'm having in FC, I have a y, and I have a morphism from C to D, so that gives me something in there. So that's the map the other way. Exercise, the composite of the two maps is the identity each way. And now, yeah, what's the important thing about it? One important thing is that, but in particular, I would have things like that. I could take for F one of these other ones. And so what does this say? Well, a functor of this shape you call representable functor. And what this says is that the morphisms between representable functors absolutely. Morphisms between representable functors are nothing new. They must already come from your original category. Okay, that means that if you have a representable functor, and you have it represented the next time, next day, then the representing objects have to be isomorphic because the representable functors are isomorphic. So, okay, now let's, so this is the principle that we will have to use a lot. And let's now just use it to introduce a symmetric algebra. Oh, maybe I should, yeah, I started to tell you about Schur, didn't I? Okay, so maybe I should say what Schur is. Schur, the K Mn modules and polynomial sorry. Mn modules and polynomial GLN modules are the same, and those of degree D form a category equivalent with the category of SND modules, where SND is the Schur algebra, so what Schur shows is that there is an algebra whose module category captures exactly what you're talking about when you're talking about polynomial representations of degree D of GLN. So there is a, so that was what, huh? No, over any base ring actually, commutative base ring. But you may have to be careful how you define the Schur algebra. There certainly are treatments that only work in characteristic 0, like I suppose his original treatment he may have been dividing by n factorial, but you don't have to. Right, but so now let me just finish with saying what is the symmetric algebra over a ring on a module. Is the C in the category of K algebras, so that the corresponding HC is the functor which to a K algebra R maps, sends the maps from the homomorphisms as K modules from M to R. Now let me see if you believe this in an example. M is K to the M. If M is K to the M, what does this mean? Yeah. R is commutative. And what does it mean? Well, you have a basis to give a homomorphism from the free module to anything. It suffices to say where the basis elements go. Now, if you take n variables, if you take n variables and you just substitute for xi the image of the basis element ei, then you get a correspondence between homomorphisms from here to there and homomorphism from here to there. I mean, the freedom that you have to take an algebra map from here, if you, to specify an algebra map from here to there, all you need to do is you have to tell where the xi go. And to specify a homomorphism from the free module here to there, you need exactly the same data. So that's the same. And so in general, if you so this shows that the symmetric algebra exists in case of a free module. Okay. Now suppose M is K to the N modulo some submodule M. Then the answer is K x1 up to xn modulo the ideal generated by M by a very similar argument. You just show that this one solves the problem. And because of Yoneda's lemma, there's only one solution. This solution is bad in the sense that you've made all these choices, but you know that they are not essential because Yoneda's lemma says that well, the basis was not part of the problem, so it cannot be part of the solution because the solution is abstract nonsense uniqueness. So I mean there is only one solution and it cannot depend on the basis, so you're okay. And yet another way of constructing the thing is if you know what a tensor algebra is. So you just form you take all the tensor powers and then you sort of make it commutative. In both cases, that should probably be a direct sum. That's a better idea, yes. And both from this construction and from this construction, you see that the symmetric algebra is actually a graded algebra, which is sort of a slight miracle in the sense that that was not part of the problem formulation. It just happens. I mean, it's not a general principle that I know why this should happen, but you compute the object that represents the functor and you find it's graded. And that's but so yeah, so here we had some examples of polynomial representations, and we sure had more interesting ones, and they correspond with what I call Young diagrams. Now, I forgot. Does anyone know if this is a French or a British Young diagram?
It's British.
This is British. Okay, so I will be British, and but I think it's time for lunch.